Okay. Hi, class. Good afternoon, or whatever time of day it is where you are. This is the third lecture for 6172, or should I say the 23rd lecture, because we had 21 mini lectures last time. I think we're going to have a lot of fun today. Clean up my space there. Okay, let's get started today. We're going to talk about bit hacks. And we're going to get started with review of how integers are represented in modern computers. So this should be review for most of you, but it doesn't hurt to go through it. If you haven't seen it, it's once again elementary, but it gets interesting fast. So to show my age, the first computer I ever used represented numbers in so-called binary coded decimal, or BCD, which you can read about, but no one uses that anymore. Today, everyone uses binary representation because the algorithms are easier and we convert between decimal, which is good for humans, and binary, which is good for machines, on inputs and outputs. Now, I say the algorithms are easier, and you don't want to estimate the power of algorithms. The Arabic positional representation for decimal numbers wiped out the Roman numeral system because it made multiplication easier, and I suppose division too. So algorithms are important, but that's enough history. Suppose that we have a W-bit word. Today, W is 32 or 64. Generally a power of 2, but the first machine that I worked on in college actually had 36-bit words. So it hasn't always been that way. It's standard to put the low order bit 0 on the right, and the high order bit W minus 1 in this case, on the left. So here's the formula for the integer x that's represented by the set of bits x0 through xw minus 1. Each bit is multiplied by a different power of 2. So you're probably pretty familiar with this. So for example, if we have the 8-bit word 100-10110, that represents, if we read from the right, 4 plus 8 plus 32 plus 128, or 150. This prefix here, 0b, designates a Boolean constant. So all numbers begin with a number, but if it's immediately followed by another character, that can indicate that it, in this case, if it's a b, it's a Boolean constant. So to represent signed integers, the computer uses the high order bit, which is bit W minus 1, to represent the sign of the number, SIGN, not SINE. But it doesn't use a sign magnitude representation. It uses what's called 2's complement, and the reason is algorithms. The algorithms the hardware implements for adding and subtracting 2's complement numbers are exactly the same as the algorithms for unsigned numbers. So you don't have to implement two different circuits for signed and unsigned. Here's the mathematical formulation of 2's complement. It's the same as the unsigned integer representation, except that the multiplier on the high order bit, the sign, is negative. Okay? So, for example, if you add 4 plus 8 plus 32, now minus 128, representing 1010110, okay? So there are 4 bits. 3 of them are the normal thing you would use for unsigned representation, but the sign bit, if it's set, subtracts, in this case, 128. Okay, so this represents the value 84. Okay, so minus 84. So whether the word 0b10101100 represents 172, which is a number I'm particularly fond of, or minus 84 depends on whether you're interpreting it as a signed or unsigned number. So this bit is the signed bit. It's important to know the range of numbers you can represent. With 8 bits for the signed case, the largest number you can represent is 127. And the smallest, most negative, is minus 128. So there's an asymmetry, 127 for the biggest, minus 128 for the smallest. But you can add and subtract them the same way as unsigned integers, as long as there's no overflow. Okay? Which is what we call it when your result can't be represented in the finite range. For example, you should watch out if you're trying to negate minus 128, or in general, whatever the high bit is. Instead of getting 128, you're going to find that negating minus 128 gives you minus 128 again, which is the wrong answer. But the reason that the 2's complement is popular is that hardware algorithms are identical, which means you don't need any special hardware. Okay, it's all in your software and your interpretation of what the bits in a word mean. Sometimes they mean signed integers, sometimes unsigned, sometimes floating point, sometimes a pretty picture. That's the magic of information. It's all just bits. And we can interpret the bits any way we like. But we have to agree on standards, and the world is all agreed on 2's complement, except possibly, I guess, flat earthers, political conspiracy theorists. Everybody else is agreed. Okay, so it's pretty easy to convince yourself that if you have the binary number of all zeros, it's equal to 0. But what if you have the binary 2's complement number for all ones? What do we get? Most of you probably know the answer, but let's just go through carefully. So this is the first line is just the formula. Okay, the sum of all the higher powers of 2, and the same for the last, except that there's a minus sign on it. And here, since all the x sub k in the summation are 1, it's just the summation on the second line of 2 to the k. Okay, and minus, since xw minus 1 is 1, 2 to the w minus 1. So, and that first summation is geometric. And you know that the sum of a bunch of powers of 2, if you add them up, you get 1 less than the next power of 2. So in this case, we get 2 to the w minus 1, minus 1. And if I subtract 2w minus 1, I get minus 1. So the word of all ones is minus 1 if I'm interpreting it as a 2's complement. And that gives us a really important identity, okay? Between the 2's complement of a number and the 1's complement. So the 1's complement, which is written twiddle x, or sometimes people say tilde x, people say both, I say both. That's the 1's complement of x, which you get by flipping every bit of x. So tilde x is just a 0 where x is 1 and a 1 where x is 0. And so if you add those two things together, tilde x plus x, you're going to get minus 1, because every position is going to have a 1 and a 0. There aren't going to be any carries, and you're just simply going to get a 1 in the output of every position. Okay, so now if I add 1 minus x to both sides of this first equation, I get tilde x plus 1 is equal to minus x. And that shows how we can compute minus x if I know how to to just complement every bit. We just complement every bit and add 1. So here's an example. So suppose we have this, this particular number. So the 1's complement has a 1 everywhere x has a 0 and vice versa. Okay, so not in the 0b prefix, of course. Okay, just in the data. Okay. Now to compute the 2's complement of x, that is to compute minus x, we just add 1 to the 1's complement. Okay, and when we do that, the carry propagates to the 4's position. So the low position is 1, 2, 4, 8, etc. And in this case, since there's already 2 1's there, if I add 1, it's going to propagate to the 4's position. And that's the result of minus x. Okay. Now we can look at this and see some patterns. Okay. So minus x is composed of the bits of tilde x up to the last 1 of x. So the last 1 of x is the one that starts the blue, okay, in the top row there. Okay. From that point on, minus x is the same as x, which is always a 1 followed by zeros. Okay, so it's identical to tilde x up to the least significant 1, and then it's that 1 followed by all zeros. Okay, so it's really fun to play with 2's complement, and sometime when you're in the Stata Center, you can check out the Digicomp 2, which is in the entry to CSAIL. Okay, this is an oversized recreation of a 1960s educational toy. The algorithm, it does 2's complement arithmetic, addition, subtraction, multiplication, and even with a little help, division. And its algorithm for negating a number is really cool. Okay, so the original Digicomp 2 was invented by an engineer named Jack Godfrey in the 1960s. It was an educational toy, and it was much smaller, made of plastic, and it used marbles as opposed to billiard balls, which this giant recreation uses. The Digicomp algorithm for negating a number is really cool. Okay, it computes it by computing the 1's complement and adding 1. In fact, right behind me here, if you can see it here, this thing here is another recreation which is smaller. And if anybody wants to stay a few minutes after class, I'll demo it for you. Now, in grade school, I fell in love with powers of 2 and binary representation. Okay, not grad school, grade school. And you can't believe my luck. Okay, perfectly by chance, my MIT office number in Stata, which is where I wish I were, turned out to be 32-G768. 32-768. That's 2 to the 15th. I'm the only computer scientist at MIT with a power of 2 for an office number, and it's not a small one at that. What are the odds, right, that I would end up in a room that's a power of 2? Okay, moving on. That was a little bit of a digression. Okay, so here's a table that shows the decimal numbers from 0 to 15 and their binary equivalents. But it turns out binary is tedious to write, so we often write binary numbers in base 16 or hexadecimal, which is much more compact. The hex digits 0 through 9 are the same as the decimal digits. They mean the same. And the letters A through F represent the values 10 through 15. Now, the reason we like hex is it's very easy to translate between hex and binary. So, for example, so it's an algorithm. That's why we like it. It's easy to do because, as you know, translating between binary and decimal is a little bit tricky, and you can't just do it in your head. Okay, so what's great is you just, to go, for example, from hex to binary, you translate each hex digit to its binary equivalent and concatenate the bits. So for example, suppose that you have the hex number decide to code for food, which is what many of you will probably do after MIT. Okay, so that turns out to be using all the legal characters. Okay, now in this constant, the prefix 0x designates a hex constant. Okay, so 0b is binary, 0x is hex. So now to convert hex to binary, you just take each hex digit and translate it to binary using the table. Or if you really have a massive brain, you can memorize the decimal to hex, the binary to hex translation. Okay, that's it. So for example, here D is 1101 from the table. Okay, so we just write 1101. E is 1110, and so we just write 1110, and so forth. Okay, really easy. And translating from binary hex is just as easy. You just translate each group of 4 bits to hex. Now, does anybody know what a group of four bits is called? Please answer in the Slack channel. A half byte, that's a good idea. That's actually not what it's usually called, at least historically. That's right, it's a nibble. A nibble. Half of a byte is a nibble. And does anyone know what 2 bits is called besides half a nibble? I guess a snack. Okay. Crumb, these are all good ideas, but they're not right. So 2 bits is a quarter. That's a joke. Okay, not really, not in computer science. But in American culture, 2 bits is a quarter of a dollar, as in shave and a haircut, 2 bits. Okay, it's a quarter. Does anybody know why a quarter of a dollar is called 2 bits? That's right, Spanish pieces of 8. So in the days of gold doubloons, which were Spanish gold coins, they're Spanish dollar, you might call them, they would cut the coin into 8 pieces or bits to have smaller units. So 2 bits was a quarter of a Spanish dollar. Okay, that's all very interesting. I love history, I love scholarship, but let's move on because we have things to learn besides our place in history. So let's dive into the main topic of the lecture, bit hacks, and we'll start with some elementary ones. So it helps to know the bitwise operators in C. So a single ampersand means bitwise and. That is, you and the corresponding bits in each position in 2 words. That's different from double ampersand, which is a logical operator that, thank you for that comment, Jonathan. That's different from the double ampersand, which is a logical operator that operates on Boolean truth values. And that's actually a short-circuiting operator in C, as we discussed last time. We also have bitwise OR, a single vertical bar, and that takes the OR of corresponding bits in a word, once again distinguished from the double bar logical OR. The caret, the little pointy thing, is bitwise exclusive OR, often called XOR, and the twiddle we've seen is the ones complement. And then the other 2 operators, the greater operator is a right shift. It moves all the bits to the right, shifting in zeros on the left. And the bits that would go off the end disappear. Now, does anyone know where the rightmost bits go when you shift them off the end in Slack? To dev null, that's a good idea. Carry, no, if we shift right, Where do they go? You got to know this stuff. You can't graduate from MIT without knowing this stuff. This is fundamental, important stuff. Where do the bits go when they're shifted off the end? Okay, got to move on. They fall into the mythical bit bucket. Okay, they go into the bit bucket. If you shift left, the less operator, zeros are shifted in on the right, and the high order bits go into the bit bucket. Okay, so be careful with shifting. And the reason is the C standard says that if the word A is a signed negative number, the behavior is undefined, and you don't want to write code that is undefined because the compiler takes a license to do anything it wants if you have undefined behavior. So if you want to shift a signed integer, you must coerce it into an unsigned integer before shifting. So that's just a warning about C. Okay, so here's our first bit hack. Suppose that we want to set the kth bit of a word to 1, leaving all the other bits untouched. Okay, so the idea is we just shift an OR. We shift a 1 left k positions and OR it with x. Okay, here's the truth table for OR and an example in which k equals 7. So we shift 1 to the left 7 bits, which makes a word with a 1 in the 7th position, because we index on the right-hand side from 0, and a 0 everywhere else. This kind of word is called a mask. Then ORing the mask with x produces the answer. Okay, it sets the bit. Okay, so why does this work? Well, wherever the mask is 0, which is everywhere except the kth bit, the output bit is the same as the corresponding bit in x, as you can see from the truth table. Okay, if y has the value 0, the output of the OR is the same as x. But wherever the mask is 1, in this case just in the kth position, the output is 1 regardless of the bit in x. So when you OR with the mask, you get the result you're expecting. So now let's clear the kth bit. Okay, so this is pretty similar, but it's just a little bit more involved. In this case, we're going to shift, complement, and rather than shift and OR. So here's an example. Here's the truth table for and an example once again with k equals 7. Okay, so let's just go through. So in every position where the mask is 1, okay, so here the mask is now tilde with the 1 shifted k to the left, okay, so shown in red. The result is the original bit of x, okay, because when you AND it, you get whatever the original, which is what the truth table shows. Whenever y is 1, the value for x just goes to the output. But if in the kth position the mask is 0, so the result in that position is 0 regardless of the bit in x. The kth bit is cleared. Okay, what about toggling the kth bit? Flip the kth bit in a word, changing it to 0 if it's 1 and 1 if it's 0. Once again, very similar. This time we shift an XOR. Okay, so we, now it turns out, and this is one of the reasons I love this stuff, XOR is one of my favorite operators, and we're going to see more examples of its use. XOR is magic. So here we go. The XOR of every position in the mask that is 0 is just the bit of x, whatever it is. Okay, so if you have 0, it gives you the same thing, but if the kth position has a 1, and then you can see from the truth table that if you have a 1 in that position, it flips the bit. So the bit is flipped in that position, and all the others are left the same. Okay. Good. So so similarly, if it's the kth bit is 1, the bit flips to 0. Good. Okay, what about extracting a bit field? That's our next thing. We're going to pull out a whole collection of consecutive bits. So the idea here is generally these things form the pattern of X ANDed with a mask and then shifted. Okay, and we use masking to extract a bit field from a word, and then we, with an appropriate mask, and then shift it the right amount. For this example, the mask extracts the 4 bits shown. So the mask that we're going to use here is those 4 bits. Okay, and you can compute them however you want, but they're shifted. You basically and that leaves just those 4 bits, and now you shift it to the right. In this case, you know, they might want to go somewhere else, but often you're extracting them to get them into something that you can deal with just as its own integer. Okay, setting a bit field is just a little bit more complicated. Okay, here's the code. So this time we AND with the 1's complement of the mask, and then we OR it with the shift. So let's reason through this with an example. We want to replace the yellow part of X with the blue part of Y. So our mask has the bits set in the positions where we want to modify X. Okay. We AND the complement of the mask, that's the thing shown in yellow on the 4th line, to clear those bits, and then we shift Y into the right position and OR the bits in. Okay, so you now see that those bits have 0, 1, 1. Okay, so we in the final answer. Now it turns out what we did is error prone. This is a dangerous way of doing it. I did it first because it's a little bit easier. But what can go wrong? Okay, so what if Y had other bits set in the word besides the blue bits, such as the magenta bit shown in this example? In that case, if we go through this code, we'd clobber something we didn't mean to. So before optimizing, you always want to write robust code. You can optimize later once everything works and you find that this piece of code is a bottleneck. So, so this solution is to AND the shifted amount with Y with the mask, so you're only looking at the books you're supposed to. Okay, and you can look at this offline. Okay. Okay, let's see, we have a query. Are these significantly faster than just doing it in the normal way? X lefted shift 1 versus 2 times X. Those are basically, the compiler is going to figure out those are the same thing. Okay, it will use shifting if you multiply by a constant like 2, and it has some really clever algorithms for multiplying by other constants. Okay, and you'll be able to look at those. We're going to see how those work. Okay, yes, swapping, yes. Coming up is one of my favorite big hacks, but first let me set it up. Okay, so you've probably had to swap 2 pieces of furniture in your apartment, say swapping your desk with a couch. To do so, you might temporarily move the desk to an empty space, move the couch to where the desk was, and then move the desk from its temporary space to where the couch used to be. And we can do the same thing in code to swap 2 values, X and Y. So here we have 3 lines of code that do that. T is a temporary that we're going to use. Okay. So here's an example. So let's see. So we first, so in the first numerical column, we have the original inputs of X and Y. And so in the second column, we compute the value for T by setting it to the value of X. So time is going to the right here. And the values of X and Y don't change when we do that. So next, we set X to be the value of Y. And so now X has the value it should. And then we shift, and then we set Y to be the value of temporary. But there's something kind of unsatisfying about using the extra temporary variable X. why can't you just swap the two values at the same time? This seems like, why do I have to involve something else? That seems strange. So this is a very clever hack. Okay, so we're going to swap x and y without using a temporary. Okay, this is hard to do with furniture, I think, but with bits you can do it. And here's the code. Okay, it's just 3 XORs. Okay, told you I liked XORs. Okay, so x gets x XOR y, y gets x XOR y, x gets x XOR y, and we've swapped them. Now I admit, and if you're not a seasoned bit hacker, this code is a little impenetrable. Okay, so let's see how it works on an example, and then we'll reason why it actually works all the time. So here are x and y, and we want to swap them. Okay, so the first line of the code XORs x and y together and puts in x. That produces a 1 if the bits of x and y are different, and a 0 if they're the same. Okay, so from left to right in the first column of bits, okay, we have 1 and 0, that's different. 0, 0, that's the same, different, same, different, different. Or what we have in the thing, if I look at it in terms of bits, 100, 10011. Okay, so that's keeping track of where does x differ from y. The old value of x is clobbered. Okay, so now we go XOR the bits of the new bits of x and y. Okay, and reading the second column of bits, we have different, same, different, 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 same, different. Okay, or 1011101. Well, that's actually magically the value of x. Okay, that's what we were hoping for. And now, one more time, in the third column, okay, we have same, different, same, different, 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 same. Okay, and when we put that in, we get the value of y. Now that's magic, and I think that's cool. Okay, so when lecture is over, maybe you can try to do that with your desk and couch. Okay, but it definitely works with. But it definitely works. So, so why does it work? Why does it work? Okay, so the basic reason it works is that XOR is its own inverse. If you take x XOR y and you XOR it with y, you get x. Similarly, if you XOR x XOR y with x, you get y. Okay, so it's its own inverse. Okay, so replacing either x or XOR of x and y essentially loses no information. I can always get it back if I have the value for the other. So having y and x XOR y in the second column, if I wanted x back, I could just XOR it with, I could just XOR y with that value for x in the second column, and I would get the original value. Okay, you can always recover the original page value. There's no information lost. Okay, so let's do it again. Okay, sort of instant replay. Okay, and of course instant replay will do it slow. So we mask the first step, computes a difference mask indicating which bits are different between x and y. Okay, that's what we end up with. So then when we do the second step, of course, y gets the value of x because we're flipping all the bits in y that are different from x. Okay, so that gives us x. And now we do the same thing for step 3. We flip all the bits in y, which are the bits in the original x, according to the difference mask, yielding the original value of y, which we store in x. So this is clearly one you'll have to play with on your own, okay? But I think it's cool anyway. As it turns out, unfortunately, this is not a good performance hack because it doesn't exploit parallelism within the processor. Each step turns out have to wait for the previous one to complete. In the ordinary swap, it turns out the processor is clever enough to pull X and Y in parallel from memory and then store them back, okay, into memory from the registers, and it can do that in parallel. So it can sort of do it in effectively two steps. Still, it's a neat trick to know, and we'll see it again later in the course. So, okay, let's learn about code branching. Okay, let's find the minimum of two integers x and y. Okay, now there are two standard ways of writing the code in C. The code in left uses a standard if conditional. So if x is less than y, then r gets x, which is the smaller of x and y, and otherwise r gets y. The code on the right is equivalent, but it uses the C question mark colon syntax, which does the same thing and is sometimes more convenient. So what comes before the question mark is what would normally come immediately after the if, and then what comes after the question mark, separated by a colon, are the two alternatives, the then clause and the if clause. Okay? With either code, you get the same machine code produced by the compiler. Okay? And what it does is the code in the machine will test whether x is less than y. That's good. But then the control flow has to branch either to execute the instruction that assigns x to r or to the instruction that assigns y to r. Now, actually, that's a lie. Okay, what I just told you is a lie. It doesn't really do that. But I guess this is the season for that kind of thing. But it isn't a complete fabrication, the way things are in this political season. So the way things were perhaps 10 or a dozen years ago, in fact, what I told you would happen. The instruction stream would branch one way or the other depending on the value of the test. The test isn't a problem, but the branch is. Okay? And here's why. The reason is that a modern processor has a deep pipeline, typically over a dozen stages, that it needs to fill in order to approach peak performance. So the processor tries to predict the path that the control flow in the instruction stream will follow, and it starts executing so-called speculatively along that path. If it predicts correctly, that's a speed up over waiting around for the result of the test before resuming the computation. But if the processor mispredicts a branch, it's got to stop, flush its pipeline, and throw away all the speculative results that it has computed for instructions it wasn't supposed to execute. So in general, if you can remove difficult to predict branches from your code, that will speed up your code. In this case, the comparison x less than y is likely to be unpredictable, which just means that the processor may not have a statistical reason to think that either x or y is more likely to be the minimum than the other, so it doesn't know which code path it's going to take. Now, modern compilers try to transfer simple code like this into code that doesn't branch, but sometimes you come across cases where not, and then it's helpful to understand what's going on with mispredicted branches. Okay? Okay, let's digress for a moment here, okay? You may have heard of the famous security bugs, Meltdown and Spectre, which got publicized about 2.5 years ago. They're really bad because they affect almost every processor manufactured in the last 20 years. And it all had to do with speculation. So normally, when a processor mispredicts a branch, it's supposed to throw away all its speculative work, so the processor behaves as if it didn't speculate. For Meltdown and Spectre, it turns out that most processors aren't quite as careful as they're supposed to be. So speculation is supposed to have no side effects that are visible on the outside if the speculation is aborted. And indeed, they turn out to be careful with the processor chip. But the computer architects were not nearly as careful about the cache system as they were about the processor state itself. So speculative reads and writes can affect the cache. And it turns out leaking information that shouldn't be seen, such as passwords, URLs, etc. You can read about Meltdown and Spectre on your own. I only mention it because unpredictable branches turn out both to harm performance and to pose a security risk. So this is not a security course. We'll let the architects fix the security flaws, and we'll look at eliminating unpredictable branches, and we'll look at predicting unpredictable branches for just the performance reasons. So back to lecture. So here's a way of computing the minimum of two integers x and y without using a branch. That's a pretty funny expression. It looks as if there's a conditional in there, x less than y, but that's actually not a conditional. There's no branching of the code. Okay, no ifs or question mark colons, just a comparison, which is fast. Comparisons are okay. It's when you use them in an if or a question mark colon, that's when you get into trouble. Okay, so what's going on here? So the C language represents the Booleans true and false with integers 1 and 0 respectively. Okay, so true is a 1, false is a 0. Well, actually, even that's a simplification. If you do a logical test of a value, a 0 is false and anything else is true. So you can test something and the thing you're testing is false only if it's 0, and if it's anything else, it'll treat it as true. But if you evaluate a logical expression, such as x less than y, the outcome is either 0 or 1. It won't give you a value other than non-zero value other than 1. Now, if x is less than y, then the part of the expression after the ampersand produces -1, which is a word with all ones. And we know that anding anything with all ones yields the anything, in which case we have the XOR identity, y XOR the quantity x XOR y, which we know is just x. Okay, so if x is less than y, hey, this produces x. Conversely, if x happens to be greater than or equal to y, then the part of the expression after the ampersand produces -0, and -0 is 0. Anything ANDed with 0 is 0, and x XOR 0 is just, and y XOR 0 is just y. Okay, so y, so in that case you just get y. Okay. Good. So then we just get y XOR 0, which is y. So amazing. Okay, a real hack. Now here's a piece of code that you might use to merge two sorted arrays in a merge sort algorithm. So let's take a look at how we can use this kind of idea. Okay, so if you have merge sort, you recall in merge sort that the merge algorithm takes in two sorted arrays A and B, in this case of lengths NA and NB, respectively, and outputs an array C of length NA plus A NB, with the elements of A and B in sorted order. Instead of using array syntax here, the code uses pointers, which makes it a little mysterious, but you should get used to that. Okay, it's usually better to use array syntax, but you'll see a lot of old code that uses pointers. That's what the asterisk can indicate. Star A is a pointer to the array A, which means a pointer to the first element of the array A. Okay. Now, there's this funny restrict keyword, which you may or may not have seen. Okay. Whoops, I lost the restrict keyword. What happened here? Okay, here's the restrict keyword. The restrict keyword means that the arrays A, B, and C occupy distinct regions in memory. The compiler doesn't have to worry that changing one of them will side effect another. which allows it to produce more efficient code. So you'll want to use restrict anytime you can. It produces faster code, okay, as long as the arrays, in fact, won't overlap. Okay, so here's an example, okay. We have these two sorted arrays. The top one, I guess, is A, and the bottom one is B, and the blue one is C. So we compare the first element of A with the first element of B. Whichever is smaller gets put into the first element of C. In this case, 3 is smaller than 4. Then the pointers to the first array are, and the output array are incremented. So we're set up for the next comparison, comparing 4 and 12. And then 4 is moved to the output. There's a little bit of C skullduggery here. See, normally the plus plus operator increments its argument by 1. Modern machines use byte addressing, however, which means that a pointer to a 64-bit word, as we have here, is actually incremented by 8 bytes with each plus plus operator, not by 1 byte. So that's a little bit of subtlety that you should be aware of. So back to the algorithm, okay? The code walks its way down A and B, always taking the smaller, moving it to the output, okay, until it gets to a point where either NA or NB is 0, that is, one of the arrays are 0, and now the last two codes just copy any remaining elements to the output. So this is a linear time algorithm, okay? The first loop is when you have something left in both A and B. The second and third loops are when one of the arrays is empty and you're copying the elements in the other. So let's look at branches in this program and see which are predictable and which are not. Now, predictable branches usually execute in one cycle, but unpredictable branches can take many cycles, 20 or more. It's pretty expensive. Okay, so let's start at the bottom. So this while loop branches depending upon whether NB is greater than 0. Is this branch predictable? That is, does it branch the same way most of the time? Okay, you want to lecture in, do you want to respond in chat? And could somebody answer Ritank? Because that's a great question. Yeah, it seems like it, okay, because basically it's predictable, okay? It's predictable because it always loops, except once at the end. So every time it goes through there, it loops. So it's only once in the execution that you might predict it wrong, okay? Otherwise, it's pretty much going the same way, okay, for most inputs, okay? What about the second one? Is this predictable or not? Yeah, it's the same reason, okay? You know, it's always loops except once at the end. Okay, what about this branch? Is it predictable? Let's see, no, this one, 3 is no. Okay, that's right. Okay, 3 is no. The hardware isn't generally going to know which element is smaller, the one from A or the one from B. And this loop generally will execute many more iterations than the other two. So there's a real possibility for diminished performance due to mispredicted branch. Okay, what about this last branch, the one in the while, in the first while? Yeah, that always loops except for its last iteration, okay? Now, there's actually two potential branches in this code, but since the short-circuiting double ampersand could represent another branch, but it doesn't matter, it's predictable. Okay, so that's yes. Okay, here's a way to remove the unpredictable branch using a trick that's kind of like the trick that we used for the minimum. It's not so important to eliminate the predictable ones because they don't take much time to execute, and you don't want to waste your time optimizing some things that won't make much of a difference. But we do want to avoid unpredictable branches and having our processor pipeline screech to a halt to handle a misprediction. So what's this code doing? Well, it's similar to the branchless minimum. We compare the first elements of A and B and put the result of the comparison in this variable CMP. It's 1 if the first element of A is minimum and 0 if the first element of B is minimum. And now we can use the branchless minimum trick to compute what the min is. And we move the A's pointer by 1 if A is the minimum and by 0 otherwise, and do the opposite for B. Okay? Moving the pointer by the logical negation, that's the exclamation point, or sometimes it's called bang, okay, of CMP. And the rest of the code is the same. And I'll let you look at this on your own. A dozen years ago, this code outperformed the code with the unpredictable branch by about 20%. But today, modern compilers actually remove the unpredictable branch for you, typically by using conditional move instructions. And the branchless code confuses them, and it probably confuses anyone looking at the code unless it's well documented. So you don't really want to optimize with these tricks unless you know what you're doing, and it's really going to pay off. Okay? So on modern machines, yeah, the compiler actually can't figure out this code as well, and they can do the optimization better than you can. So, so the compiler knows whether a branch is predictable by looking at what the structure is of it. It realizes it's going to exit, for example, from those from 1, 3, and 4. It realizes that it can only fail once, so it has a good idea of what it is. And also, the hardware does prediction. And the hardware does it dynamically. It looks to see which way you're branching most of the time. Okay, and it stores that information in the processor state. Okay. Okay, so this, I'm sure, has come up. Why learn BIC hacks if they don't even work? Okay. And there's a bunch of reasons. First, the compiler does them, and it'll help you to understand how the compiler is optimizing your code when you look at the assembly code or the compiler intermediate representation. Sometimes the compiler doesn't optimize, and you have to optimize your code by hand. Sometimes the bit hacks for words actually extend naturally to bit, byte, and word hacks for vectors. Okay, so you may want to use the trick even if which maybe the compiler doesn't deal with. And these tricks turn out to arise in other domains, so it pays to be educated about them. And finally, because they're fun. Actually, there's one more reason. Bit hacks will help you on Project 1. That may be the most important reason from your short-term point of view right now. Okay, let's look at modular addition. Okay. Here we want to compute the sum of two numbers, mod n, and let's assume that they're both non-negative. So in C, you can express that as x plus y and then a percent sign. But that requires a division, which is generally expensive to compute. Okay? If it turns out that the compiler knows that n is a power of 2, it does something simpler, or if it actually knows what the constant is, it can do something more clever. But otherwise, it's going to do a division, which is 2 to 4 times the cost of an integer multiply. By the way, you should know that in C, the percent sign is not the mathematical modulo operator. It is the remainder operator, and speaking as an applied mathematician, I think it's a fundamental design flaw embedded in most computer language. And here's where percent kills me. If x plus y is negative and n is positive, your answer is a negative number. Okay? It's not the least positive residue when you divide. Okay? It's a negative number, and that can be painful to forget, and it's not mathematically clean. Okay, so that's my rant. In this case, however, we're assuming that x and y are both non-negative, and in fact, neither is equal to n or greater. That means their sum is at most n minus 2. And we can avoid division by just using this code. We add the two numbers together, okay? And if the sum is less than n, we return that sum. and otherwise we subtract n from it, okay, because we know it's not going to be bigger than n minus 2. Okay, so we can use, now we can use a trick, the same trick as minimum, to do something similar, and I'll let you work this out. Turns out when I compiled this with a compiler, they give exactly the same output code. Okay, the compiler does this trick. Okay, well, it doesn't quite do this trick, but it realizes what it needs to do and it does the same thing. So it's actually not any faster. Yet another example. Okay, let's move along. So you can play with those more. Okay, let's talk about powers 2. I told you I love powers of 2. Okay, so let's look at some of the bit hacks involving powers of 2. The first is something you often have to do, which is round up to an integer to the next power of 2. Now you can do that with a loop. That's a really lousy way. Okay, what we, in mathematical notation, we're computing 2 to the ceiling of log n, where log is the LG log, which means log to base 2 of n. Okay, so that's a power of 2 because 2 is, it's 2 to an integer. Ceiling of log base 2 of n is an integer. And it's the first power of 2 greater than or equal to n. Okay, and so that's the notation. Okay, so here's a way of doing it. Okay, we subtract 1 from n, then we OR n with n shifted to the right 1 position, then we OR n shifted to the right 2 positions, then 4, 8, 16, 32, and then we increment n, and that's our answer. Okay, pretty straightforward, right? Okay, let's see what's going on. With an example, we start with this number. The answer should have a 1 in the second bit position. That's the next largest power of 2. Okay, so the 1 in the second bit position on the left. So let's execute the code, see what it does, and then reason about it. So we decrement the number, so that borrows out of the 5th position from the right and produces a 1, 1, 1, 1 there. We then shift right 1 position and OR. Every position that has a 1 now has a none next to it to the right. Okay, that's what that did. So if it had a 1, it now has a 1 in the same position, and it has a 1 right next to it. Now we shift right 2 positions and OR. And now every position that originally had a 1 has 3 more 1s to its right. And we shift 4 positions and OR, okay, and 8 positions, and we can see the effect of all that shifting and ORing. We propagated any 1s to the right, flooding the lower order bits with 1s. Okay, 16 has no effect because we're operating on a 16-bit number, not a 64-bit number. Okay, and similarly, 32 has no effect. Finally, we add 1, and we have our answer. Ta-da! Okay, why does this work? So why decrement to begin with? Well, so you can sort of see what we're doing. We're basically flooding the bits to the right, but we have to take care of the case where n starts out as a power of 2, in which case it already has the 1 set in that second bit position from the left. So we want to make sure that it can't be there. So by subtracting 1, we're going to be fine. Okay, and then we go and we we make sure that bit log n minus 1 is set, ceiling of log n minus 1 is set. And then we go and we flood all the lower order bits. And then we set bit log n minus 1, because up to that point, every bit less than the ceiling of log n bit is 1. Okay, once again, some of these you're going to have to sit down and study. Okay, here's one of my favorite bit hacks. Okay, compute the mask of the least significant 1 in a word. And this is really easy. You just take x and you AND it with minus x. This is really weird because you're doing, logical operators on a negative number. I mean, it's just plain weird, okay? But it's really simple. Okay, so let's see. So this is the first number, so x is the first number here, minus x is the second number. And when you add them together, you can see you get a 1 just where we want it. So why? Well, remember that the binary representation of minus x is the complement of x plus 1. Okay, so it's 1's complement for the high order bits down to the least significant 1, and then it's 1 there and 0 for the rest. Okay, so that ends up meaning that's the only bit that's set. Every column ends up with a 0 and 1 that is above the bit. Then you have 2 1s, and then every column ends up being a 0. Okay, and so when you AND them, you get just a 1. Now, the more interesting question is, how do you find the index of the bit? That is the log of r. So r here, the bit log base 2 of r, where in this case r is a power of 2. Okay, how do we get that bit? Okay, and so that's our next problem. It's essentially log of x, where x is a power of 2, is essentially counting the number of trailing zeros. Okay, here's the code. I'm sure it looks familiar. Okay, you've seen this before. You first set the constant de Broglie to hex 022F DD63CC95386D. Then you have the standard table lookup. All you do is multiply x by the de Broglie constant, shift right 58, which of course is the natural amount, and index the table. Okay? You've all seen this, right? Just kidding, okay? When I look at this code, I say, you know, this looks like magic. Okay? And usually at this point, I do a Mathemagic card trick with students from the class to demonstrate how this code works. Okay? But unfortunately this year, with COVID and all, I can't do a live magic trick for you. So we'll put up a video of last year's magic trick on Canvas that you can look at. Right now, I'll just explain how the code works. It is magic, and the magic trick really shows how magic it is. Okay, so why does it work? So a de Broglie sequence S of length 2 to the k is a cyclic 0-1 sequence such that each of the 2 to the k 0-1 strings of length k occurs exactly once as a substring of S. Wow, is that a mouthful? Okay. Let's see what that is. Okay, so here's an example with k equal to 3. So the de Broglie sequence we're interested in is going to be at a de Broglie sequence of length 2 to the 3, or 8. And the number I have at the top of the blue rectangle there, that's a de Broglie sequence of length 8. 0, 0, 0, 1, 1, 1, 0, 1. Now, if I look at each group of 3 bits cyclically shifted, notice that the pattern never repeats. And in fact, they go through each of the 3-bit positions, 3 of the 3-bit values that you can have with 3 bits. There are 8 different settings for 3 bits, and every one of those is a substring. Okay? And so that's the property of a de Broglie sequence. And that in that big complicated code, I had a de Broglie sequence of length 64. Okay? Now, the convert table, which here I've just done for 8, translates from the 3 bits, okay, from each of the 3 bits, depending upon the rotate amount, to the amount needed to put those bits in the higher position. So, for example, if I see that I have the higher order bits, if I've done a cyclic rotation of the de Broglie string, then if I have a 0, 0, 0 in the high order bits, I know I didn't rotate at all. If I see a 0, 0, 1 in the high order bits, I know that I rotated 1. If I see a 1, 1, 1, 0 in the rotated bits, then I know I rotated 2, and so forth. And so this table just converts between what those bit strings are and what the actual rotation is. Okay. So, so now what goes on? Well, I take the De Bruijn sequence, I multiply it by, in this case, it was a 1 in the 4th position, so that's 2 to the 4th. And what does multiplying by a power of 2 does? It just does a shift, okay? And it rotates zeros in on the bottom. So it's the same as if I had rotated the whole word, and now I want to extract the top 3 bits, which in this case I can get by shifting by 2 to the k minus k, or in this case 2 to the 3 minus 3, which is 8 minus 3, which is 5. And when I do that, I get a 6. And so when I convert 6, I get a 4. That's what I'm supposed to get. Okay? So this code, you can look at it on your own, is pretty clever, okay? And it's also only involves a table lookup and a multiply, and everything else is sort of single cycle stuff. Okay, so it's really, really fast. Now, it turns out most modern machines have a hardware instruction that does the counting trailing zeros, and you can access it with the compiler built-ins. Here's the one for an int, and there are ones for the other integer types to do it, and that's going to be much faster than doing it by hand. Okay, but some people may work with embedded processors that don't have a sophisticated instruction set, and then these kinds of things can be really useful. Okay, so that's the trick. Okay, now we're going to see a really fancy bit trick, but it's going to take us a couple steps to get there. This is pop count. Okay, pop count is counting the number of ones bits in a word X. Okay, I'll ignore the naive algorithm. It just checks every bit one at a time and adds 1 to the answer if it happens to be a 1. Instead, we can use a bit hack to repeatedly eliminate the least significant bit, okay, which speeds things up a bit. Okay, so here's the bit hack. Okay, it basically goes through the word starting R with 0 and incrementing it, and we keep going until X, which is the input, which we're going to side effect, is not equal to 0. Okay, and in each stage we AND X minus 1 into X. Now, what does that do? Here's an example. If I have X and I have X minus 1, similar to the minus X thing, okay, but a little bit different, X minus 1, you can verify, has a 0 in the least order bit of X, and it's the same as X for larger, and it's 1s when X is smaller, but X is 0 for smaller. So when you AND them together, okay, you clear that bit of X. Really clever trick. And so we just loop through that, clearing 1 bit at a time. Okay? If the pop count, if the number of ones is small, this algorithm is great. But asymptotically, it's no better than the naive algorithm we ignored, okay, if the number of bits is large. If it's a random word, for example. Okay, so here's our second attempt. This is a table lookup. We make a table, auxiliary count table, where the ith entry is the number of ones in the 1-bit value I, that is the 1 byte pop count. So 0 has 0 ones, 1 has 1 1, 2 has 1 1, 3 has 2 ones. That's how we're getting the entries of that table. Okay, and of course you could compute this with a little metaprogramming. Okay, all the way up to 255, which has 8 ones. The algorithm runs through the bytes of the word, extracting each byte and adding its pop count to the total. Okay, so pretty simple algorithm. The performance, once again, scales with the word size, but the constants are potentially better because we're processing by bytes instead of bits. Now, unfortunately, we can't make the count table too much bigger because it starts to get expensive to access it. So here are some typical access latencies for different parts of memory. A register you can get in one cycle. In fact, you can get multiple things in one cycle, okay? Multiple registers in one cycle, the processor can. The L1 cache is typically like 4 or 5 cycles. The L2 cache, 10 to 12 cycles maybe. The L3 cache is maybe 40 cycles. Some are like closer to 30, but it could be as much as 50. And the DRAM is like 200 cycles, and it's sort of minimum these days would be 150. So it's a lot. It's way bigger when you go to DRAM. So the bigger you make your table, the less likely it's going to end up in your L1 cache, okay, which typically has like 32K bytes in the data cache, okay? So, so you can't make this go arbitrarily large. Okay, here's the fun one. Okay, here's a third algorithm, which I've shown for 64 bits, for 64-bit words. It uses parallel divide and conquer. Really cool. It creates initially 6 masks, and if you look at the bit manipulations, M5 has a group of 32 zeros and 31 zeros. Okay, so I'm using the notation here. X to the K means just repeat X K times. Okay, well, it's a different X. I shouldn't have used X. I should have used a different variable. Sorry about that. Okay, so then the next mask has a group of 16 zeros, then a group of 16 ones, 16 zeros, and 16 ones. And the next one is groups of 8 bits, zeros and ones alternating, and then 4 bits, then 2 bits, and finally just 1 bit, just alternating 0, 1, 0, 1, 0, 1 for M0. Okay, so let's see what's going on with this example. Okay, and then we use that in a particular way that I'll show you in a minute. So let's take a look at how it operates. Okay, here's a 32-bit word, but you'll get the idea for 64. Okay, so we won't have to actually do the last step. Okay, we compute these 2 intermediate. So remember, in M0, the bits alternate, 0, 1, 0, 1, 0, 1, 0, 1. So when we do that, and my animation failed here, and I couldn't correct it in time, but it works for the other ones, you'll see. So the first line, X and M0, is just all the ones that the positions where M0 is a 1, we extract, and then we shift the max left and end it with M0. Sorry, we shift the X right and end it with M0, and that extracts all the odd numbered bits. So we get the even numbered bits for the first one, the odd numbered bits for the second one, and then we add them. Okay, and when we add them, we get this. Okay, well, what is that? Who knows what that is? Okay, let's see. Okay, we can understand what that is if we look at this in groups of 2 bits. What we've done is we've added up the number of ones in each consecutive 2-bit field. We've partitioned the word into 2-bit fields, and then we've simply added the ones in, the ones, we've added up the number of ones. So for example, the first column has 2 ones, and so now we have represented a 2. And the next column has 2 zeros, so we represent a 0, and 2 zeros again. And then the next one has only 1 1, so we represent a 1. Okay, so that's what that first step has done. Now we go to the next one. So we mask and shift and now we add those 2 together. And so what we get, this number, is just the bit representation of where every 4 bits says what's the pop count of those 4 bits. Okay, so 2 for the first column, 1 for the second column, 2, etc. And we do it again. Okay, and we get now every 8 bits. Okay, so now every byte has the pop count of that byte. And we continue. Okay, and continue. And continue. And we don't do the last step because we only have a 32-bit word. Okay, but that's the result, and we have our answer 17, which if count up is the number 1. So this is classical parallel divide and conquer. Okay, very clever. Now, of course, let's take a look at this code again. Okay, so here's the original code. Okay, so the performance here is log W time, where W is the word length. So that's much better than order W time, which the other ones were. Okay, and moreover, it's pretty much all done in registers. The constants are excellent for this code. Okay, you might wonder why we have extra masking for the first two steps. Okay, you see that the first 2 steps after the pop count. Okay, and the reason is that avoids overflow, and you can look at that. If you're not careful when you add those 2 things together, you might corrupt another field. But once you get numbers that are small enough relative to the field, you can't overflow out of the groups, and so you don't need to do the extra masking. Okay, so pretty good hack. Okay, no worry about things. So most modern machines provide pop count instructions, which operate much faster than anything you can code yourself. Okay, and you can access them once again via compiler intrinsics, for example, in Clang. So here's here's the built-in for pop count. You have to be careful. In some compilers, you may need to enable certain switches to access built-in functions, and your code may be less portable. And here's a little exercise that you can do on your own. Compute the log base 2 of a power of 2 quickly using a pop count instruction. Okay, the last one I'm going to do is a classic puzzle, and by classic I mean it's, get this, 172 years ago was when it was invented. Now, 172, that's a curious number. Okay, as I said, that's internet, and that's amazing that just happened to be the number. How many years ago this puzzle was invented? I was stunned when I saw that. I am one lucky numerologist. Okay, so someone in someone in 1848 named Max Bezel created this puzzle. And it turns out even Carl Friedrich Gauss, the greatest mathematician who ever lived, worked on this puzzle. So just amazing, what it was. So it turns out that with modern computers, this is a really good one to solve. So what's the problem? You've got to place n queens on an n by n chessboard so that no queen attacks another. Okay? Now, if you don't know chess, here's how a queen attacks. It attacks everything in its row, column, and diagonals. Okay, so in other words, this says no 2 queens can occupy the same row, column, or diagonal. And we want to find all the ways of doing it. And this is one example of a very nice symmetric way. They're not all symmetric, but this is a nice symmetric way of solving the 8 queens problem. Okay, no queen attacks another if you check. And we want to count how many there are. So our strategy is to write a typical backtracing search. We try placing the queens row by row. And if you can't place a queen in a row, you backtrack. So we start with the first row, and we place a queen. And then we move to the second row. And then we try out all the positions a queen could go. And if it can't go there, then we go to the next one. It doesn't go there because it would share. Okay, so there's no point in exploring any more things if we can eliminate it from consideration as being part of the solution. And so now we go to the next one, and it searches across. And then we go to the next one, and it searches across. And then the next one. Can't go there, can't go there, can't go there. Keeps going. Okay, then the next one. Can't go there, can't go there, nor there, nor there, nor there, nor there. Oh, this isn't looking good. Okay, this is when we backtrack. So it turns out that that queen we just last placed, there's no arrangement with those first 4 queens position that the 5th queen can be positioned there. So we just continue with that row. We backtrack and continue, go backwards to the previous row. And we found a place. Good. So now we go again, checking all these guys. Keep going. Keep going. Nope, doesn't go there. Nope. Uh-oh, stuck again. So we backtrack again, okay? But we're at the end of the row. So we have to backtrack again. We can't have anything that starts with those 4 queens, and so the last one is the one that we want to do it. And we keep going, okay? And so that's how backtracking search works, and it's easy to write a little recursive program that'll enumerate all possible solutions using that. But we want that to go blazingly fast. So how should the board be, the question I'm going to ask is, how should the board be represented to facilitate queen placement? So the first thing you think about is, well, let's use an array of n squared bytes, okay? So we have an n by n matrix, and each byte holds a queen or is empty. And then you think, oh, there's only 2 values. So instead of an n squared bytes, we could use n squared bits to say where the queens are. Okay, because now that's better, but as you think about it, remember that every row is only going to have 1 queen. So we could just use an array of n bytes which store the position that the queen, if any, that the queen in that row is in. So we have an array of n bytes where the first element is the position of the queen in the first row, the second, the element of the queen in the second row, and so forth. Okay. I'm actually going to share a neat hack that uses only 3 bit vectors of size n. Bit vectors of size n. And that conveniently fits in a 32-bit word typically. If you try to do things bigger than 32, you're probably not going to complete the search, okay? Because the number of the search space gets bigger exponentially. So here's the idea. Here's the bit vector representation. So we're going to have 3 bit vectors. One of those bit vectors is we're going to use the variable down, and down tells which columns have queens in them. Okay, so here, if I have down, if I look at the first column, down is 1 because there's a queen there. Or so I look at well, that's the 7th column, I guess. But if I look at the 3rd column, because we're indexing from the right from 0, okay, that has a 0. So that's a safe place to put a queen, okay, at that point. Okay, so placing a queen in column C is not safe if down and the position you want to put it in, okay, which is the bit mask for that position, is not 0, okay? So where the place is whatever the column is we want to put in it, left shifted, we have a 1 left shifted by that amount. Okay, so if column C is safe, then we can update it just by doing an OR equals, okay, updating down with the value of place for the next row. Okay, so in this case we would get a 1 in that position. Okay, so if we if column C right now. The other 2 vectors, one is left, which looks at left diagonals, and the other is right diagonals. So left diagonals, it's not safe. Similarly to if you're doing columns, we're looking at diagonals going across. So all these numbers are basically the diagonals, okay, that, and it says whether or not it's safe to put something there. It's safe if there's a 0 in it, and otherwise it's not safe, okay? And similarly, if you've got nothing in it, then we get a 0 in those positions. Okay, and we can play the same game for the left diagonal, the same as we did for down. And then the right diagonal is similar. Here we go. So, okay, so those are the 3 bit vectors we're going to do. Okay, and I'll let you look at this on your own. Here's the code. It's amazing. This is inspired by a little code snippet that Tony Lazard in 1991 sent in an email that got widely distributed. Okay, it basically just goes down And if you look at this, it's amazingly short and fast. You just go down to a few bit operations on your variables and then call yourself recursively. The compiler puts almost everything in registers except possibly for the subroutine linkage. Amazingly fast. Amazingly fast. And it really zips. Okay, some final remarks. Okay? So you might ask if those are all the big hacks that there are. Well, I'm glad you asked, okay? Because the answer, of course, is no. Here's some further reading. So Sean Anderson's website is a good summary of bit hacks, and he's got 32-bit code. So it's a little old, 32 bits, not 64, but most of the ideas scale. Knuth's Volume 4A has a section on bit manipulation, and the Chess Programming Wiki is a great repository of information about programming computers to play chess. And we're going to be doing a chess-like game, so it doesn't hurt to get familiar with it a little bit. And it's got lots of bit hacks. And Warren writes some floating point bit hacks as well as integer ones. Okay, so it turns out you can play with floating point numbers too. So to close, I want you to finally remember to support computer science, because every little bit counts. I'm probably lucky I can't hear the groans. Okay, for those who want to see the Digicomp 2 demo, hang on. Everyone else, so long till next time. So let me stop the screen sharing and switch cameras, and I'll try to show you how this thing works. So this is going to be live demo, which is guaranteed, as you know, live demos are guaranteed to fail. But we will focus in on the whoopsie, what happened to my Zoom meeting? There it is. We're going to focus in on a different camera that I have on there. So let's see here. I need to change my video to that video camera. Now, did it do it? Oops, nope, I forgot to save the position. Of course, there's always going to be something going on. So let me adjust this. Okay, so so Alex or Ravi or somebody, can you help me get this so that I can look at the, because I can't really see my thing very well. So let's see here. So I want to go down a little bit. Is that right? And I want to go over a little bit, I think. Do I have it? Oh yeah, there it is. Got to zoom out a little bit. Okay, and maybe up a little bit. And can you see I can't tell if you can see the bottom there or not.
Yeah, that's good.
Okay, and then we'll make a little room for me. Okay, so this is basically isomorphic to the machine in the Stata Center. Okay, so how are we doing?
You might need to rotate right to show yourself, Charles.
I need to rotate right. Rotate what right? Oh, I did it the wrong way. I did it the wrong way. I'm showing the supercomputer board, not the how's that?
There you go.
Is that good? Can you see the bottom of the? No, you don't have to see the very bottom, but you can see the main part. Okay, is that good? So you better be on speaker view if you want to see this, because otherwise you're probably going to miss something. I think I'm going to put myself on speaker.
I spotlighted your video.
Okay, good.
No, I think it should be on.
How come I don't have it? I need to set speaker view. Great. Okay, there we go. Now I can see myself. And now I'm going to, in fact, go full screen so I can even look over and see myself. Good. Okay, so this is the Digicomp. Digicomp 2. There's also a Digicomp 1, interestingly. Okay, so let's see what this does. So the main part of this, let me see here, is this bank of registers here. Okay, this is the accumulator. And what Jack Godfrey noticed was that with these little toggle things, that it would count if you fed one into the next in the appropriate way. Okay, so let's watch this. It's actually better to use the big one because the big one's a lot slower. This goes actually kind of fast. Okay, so let's see. We're going to start counting marbles. So the first one goes through, and it sets the low order bit. That's the one at the top. And that triggers the next one, which clears the first and sets the second. And now the second one sets the next. And now I've got 4 balls, and 5, and 6, and 7, and we'll do one more, and 8, and you get the carry all the way down. Now, is that cool or what? Very, very cool. Okay, so that's how we, that's how it can count. But this thing actually can do addition and multiplication and 2's complement, interestingly. Okay, so let's see. Which should I do first? Let's do 2's complement because that's the one that's really cool, and which I think is very cool. And then I'll show you multiplication because it turns out it does a multiply add. It's a fused multiply add FMA instruction that it does. Okay, so let's see. So we want to program into the register here some bit value. So what's a good bit value to do? We want to have some, let's see, I think we want to have something like, let's do something like this. How about that? Okay, that's a negative number. Okay, what is it the negative number of? So can somebody compute that quickly? So we have the number from left to right is 1, 0, 1, 1, 0, 0, 0. Okay, so what's the 2's complement of that number? Can somebody, one of the TAs or Jonathan or one of the students? So unmute everybody because they might as well talk. Okay, you see what the number is and what's the 2's complement? This you got to be able to do in your head. Okay, so it's the complement of the high order bits, remember? And then when you get to the least significant 1 bit, that stays 1, and then all the rest are zeros. So in this case, we should get 0, 1, 0, 1, 0, 0, 0. I agree. So did I say that right? So 0, 1, 0.
I think you need to complement that third bit, but.
What's that?
I think you need to complement the third bit, right?
So what did I say? I said 0.
So it's
right. It
0, 1, 1, 1, 0, 0, 0. Yeah.
It's right. Okay, good. Okay, well, let's do the calculation because that's more fun anyway. So to do that, I configure these switches. So I set the, let me see if I remember how to do this. So I set the complement one on here. Okay, that says complement on. And I set this one to this way so that it's doing the complement. Okay, and now this is really good. So you notice that when I was carrying things down here, these channels over here, whenever there was a carry, whenever I flipped something from a 0 to a 1 and there was no carry, the ball just rolled down all the way, right? And that made sure that it didn't increment things below. So the way this does 2's complement is the way we learned today, which is it's going to complement all the bits, and then it's going to add 1, okay? And it complements all the bits by making it so that regardless of whether it's a 0 or 1, when it toggles it, it goes into the next one. So let's see how that works. Okay, here we go. Ready? I hope I've got it set up right. Okay, so here we go. The first thing it does is it resets all those little flippers to be the other direction. Whoops. Oh, because I had it on manual. Okay, I had it on manual. I knew I hadn't set something up. So this is going this way. now it flips all the bits. So now we have the, oops, I have that set to the wrong thing too. Okay, let's do this again. Okay, I want to get it so it does it right. So what was my number? 1, 0, 1, 1, 0, 0, 0. And I think now I've got everything set up. Is that right? 1, 0, yeah, and then these guys all have to be the other way. There are little markers on here that show where it's got to be. Okay, so let's try again. This time it's going to do it right. Okay, so you can see I'm not a great programmer. I make errors. Okay, but that actually makes me a great programmer because I'm so afraid of making errors, I write really robust code. Okay, let's try again. So I've got it on automatic this time. I've got complement on. I've got this in the complement position. I've got everything. Okay, I think we're good. Let's try this again. Here we go. So we clear all those things. And now this allows every bit to be one's complemented, see? And now it goes through, it clears all those ones on the side, and now it adds 1. Okay? And so you see, we get the answer that we're supposed to have, which is 0, 1, 0, 1, 0, 0, 0. Okay? Now, is that cool or what? That's amazing that you can do that. But wait, there's more. Okay? This machine will multiply 2 numbers. Now, it doesn't use the shift and add algorithm that that you might think. Instead, it does it in the oldest possible way. It does it with repeated addition. Okay, so let's see here. So let me explain what goes on here. So let's first of all clear the. So we're going to run the clear function. So put that on there. And now if I click this, it's going to clear everything. So my register is now clear. Okay. And we're going to need some more balls for this. More marbles. So the Oneness Data Center is really cool because it has billiard balls. And it's just like, they're big. It's totally cool. And it doesn't run as fast. This is a place where like miniaturization really makes a difference. This is runs so much faster than the one in Stata because the one in Stata
because we're still in the Dennard scaling regime.
Yeah, right, exactly. Exactly, right. We're not approaching the speed of light of the balls or anything. Okay. And I have some more here. Put in. Okay. So let's multiply 2 numbers. Now that's what these other things are. So let's multiply, let's say 3. We're going to turn this on, multiply. Okay, so that's a multiply. Everything else is set up right. And we'll multiply 3, which is, there's a 3. Okay, and the 1 plus 2 is 3. This is the 4th position. And then over here, these guys are going to be what you multiply by. So let's multiply 3 by, let's say, 10. Okay, so 3 times 10. So we should get the answer if the hardware doesn't screw up and the operator doesn't screw up. We should get the value of 30 when we're done. Okay, in this register. Okay, and if we have something initially in this register, okay, then whatever else is coming will be added. So let's take a look at what's going on here. So these 3 flip-flops are distributors. What they're going to do is, if you look at where these things are going, either you're going to have a ball channeled into the 1, 2, 4, or 8 position of this register. Okay, or not, depending upon the setting of these guys. Okay, and these basically take it through a cycle where it goes one by one to each of them, but it doesn't go in the normal order. It goes in an interleaved order, as you'll see. Okay, so this over here is very much like the incrementer circuit, except it decrements. Okay, it goes down by one just by toggling. Okay, so pretty much it's the opposite of these. Okay, because incrementing a negative, it's like having negative numbers, and I just increment it. Well, that's actually decrementing it. Okay, so maybe I'll run it on manual for one step, and then we'll let it go automatically. So the first step, okay, it goes through, and it decrements the multiplier here, and that is it doesn't decrement it to 0, so therefore it sent a ball through the 8 here, and that was the first one that it went through, was the 8, and it added, in this case, an 8, one of the bits of this number, into the sum. So we now have 8 in the sum. So now we go ahead, we'll do the next bit, and so when I get this running, it will run itself automatically if I put it on auto. So now it adds in a 2. And so notice now at this point, we have the 10 we want in the accumulator. Okay, so 10 is in the accumulator, which is what we wanted to add in for the first time. But it still has to keep going, and so it now looks at the 4 position. And the 4 position, since it's a 0, the ball just drops through and doesn't affect anything. And similarly for the 2's position. Okay. And now I'll let it run itself to the end. Okay, so it just added in 1 10, and it decremented that once. So now it's going to go through, going to do the same thing, and we'll see. Okay, so now it decrements that again, adds in a 1, adds in an 8, adds in a 2. What happened there? Oh, I had the complement still on. Darn it. Okay, my bad. Okay, we have the complement on. Okay, so we can keep going. Okay, we don't add in on the 4s, we don't add in on the 1s. Now we decrement again. Okay, again. Hope I didn't screw it up with that. Boneheaded not observing the complement on. And now it discovers that 0 shows n. So what do we have in the end? We have a 16 and an 8 and a 4 and a 2. Okay, so 16 plus 8 is 24, 28, 30. We did our multiply. So that is the Digicomp 2. It's the one in Stata, you can play with it. It's a lot of fun. Being a mechanical device, it sometimes has some issues. I haven't been in Stata since March, so I don't know, before I left, I covered it up, but I hope that it's going to be in good shape when we get back. It certainly has been running very effectively for the last 5 or 6 years. Are there any questions?